Welcome back to the Deep Dive. Today we're moving past typical home entertainment setups. We're really plunging into the kind of heavy-duty infrastructure needed for, well, mission-critical video. Think command centers, huge monitoring walls, places where, every pixel and every second truly counts. Our focus, high-capacity, 4K 60 HDMI Matrix switchers, the real backbone stuff. And our mission for you, our listeners, is to kind of pull back the curtain on this tech. How do organizations route dozens of ultra-high-def sources to potentially dozens of displays instantly?
Yeah.
Without dropping a single frame?
Exactly. And we're grounding this whole discussion in some specific technical blueprints. Yeah. We're looking closely at the specs and setups for WolfPack 4K 60 Hz HDMI Matrix switchers from HDTV Supply. And it's worth noting, this isn't some newcomer. The company, they have a 24-year track record, global stuff, certified since 2003. And importantly, they're an HDBaseT.org approved adopter. That kind of background, it suggests this gear is designed to tackle some seriously complex distribution challenges.
Okay, complexity. Let's start unpacking that. First hurdle, image quality. These are massive systems, but you can't sacrifice clarity just because you're scaling up, right? So what's the baseline? What's the fundamental signal standard they absolutely have to maintain?
Yeah. There's no compromise there. The standard is 4K resolution at 60 frames per second with 4.4.4 chroma subsampling. And crucially, that requires a data rate of 18 gigabits per second. It's a huge pipeline.
18 gigabits,
yeah.
And that 4.4.4 number. It sounds technical, but why is that specific detail so non-negotiable in these high-stakes places?
It's all about the color information, the chroma. 4.4.4 means zero compression on the color data. You get the full picture, every single nuance. Think about, say, medical imaging or maybe detailed satellite feeds, complex maps.
Okay, yeah.
If you use the more common 4.2.0 standard, which saves bandwidth, you're actually throwing away some color information to compress the signal. In the control room, that lost detail, it could genuinely lead to misinterpretation. Critical mistakes. So 4.4.4 at 18 gigabits ensures the complete visual dataset reaches the display. No compromises.
Got it. Full fidelity.
And running alongside that bandwidth requirement are the compliance standards, modern ones. We're talking HDMI 2.0, that's what mandates the 18 Gbps bandwidth, and HDCP 2.3.
Let's pause on HDCP 2.3 for a second. Copy protection. Why is that such a potential point of failure in a mission-critical setup? Seems counterintuitive almost.
Well, it's more than just stopping piracy in this context. It's essentially a digital handshake. Every single device in the chain, the source, the switcher, the cables, the display, everything has to support and successfully negotiate that HTTP 2.3 protocol. If just one link in that chain fails the check, the source material, like a secure server feed, might just refuse to send the picture. Blank screen.
So it's a system integrity check, basically. Non-compliance means operational failure, not just a fuzzy picture.
Exactly. You could have the best switcher in the world, but if it can't pass that HDCP check with both the source and the display, you get nothing. So the architecture has to juggle this massive data volume and these strict security protocols simultaneously.
Okay, so that defines the signal quality and the security layers. Now let's talk scale. How does a matrix system actually manage routing that pristine, secure signal everywhere it needs to go? Flexibility must be key.
It is. The whole philosophy behind these systems, as the source material puts it, is modularity. The goal is any source to any TV, any way wanted. Pure flexibility.
Right.
So an operator can take, input 3 from a camera feed and instantly send it to output 12, which might be a single monitor. Or they could send input 5 from a server rack to outputs 1, 2, and 3 simultaneously if they're part of a video wall.
And the maximum capacity mentioned in the specs is, well, it's pretty impressive. These systems are built within an 18 by 18 chassis. That's potentially 18 inputs feeding up to 18 different displays.
Correct. Up to 18 sources, up to 18 displays. But just routing isn't the whole story, especially when you get to that scale. Managing 18 distinct outputs often involves more than just simple switching. You need processing power, particularly for video walls.
Ah, yes. The video wall feature.
Exactly. And this is where these switchers show they're more than just routers. They have integrated video wall processing and scaling. This means the system itself can take a single source and intelligently split and scale it across multiple displays. The specs say it supports video walls of any size or quantity. They give an example of a 3x3 setup, so 9 TVs acting as one giant screen.
Okay, that makes sense for command centers.
Yeah.
But there was one feature mentioned that seemed almost odd. Support for 180-degree TV flipping. That sounds like something an installer deals with, not the switcher itself. Why integrate that?
It's actually quite clever. It solves a common physical installation problem. Sometimes, especially near ceilings or with tricky mounting brackets, it's much easier for installers to mount a display upside down for better cable access or weight distribution.
Yeah. All right.
Normally, you might need a separate little box, a scaler or rotator behind the TV to flip the image. By building that 180-degree flip capability directly into the switcher's output card, you eliminate that extra piece of hardware, that extra point of failure, and the extra cost. It streamlines the installation.
Interesting. But that does raise a question, doesn't it? Integrating complex processing, like scaling and image flipping right inside the switcher. That takes processing power. Doesn't that kind of internal manipulation usually add delay, latency?
That's a very sharp point.
Yeah.
Yes, internal processing can introduce latency, and in mission-critical settings, latency is the enemy. So the system specs really need to prove that it can handle this processing without slowing things down noticeably.
Okay, perfect transition then. Let's move from the what definitions and processing to the how. How do you physically move that 18 gigabit per second signal potentially across a large building or campus? You can't just use a standard 10-foot HDMI cable everywhere.
Definitely not. And that's where the modularity comes back into play. For short runs, maybe within the same rack or room, you can use standard HDMI input and output cards in the chassis. Simple. But for longer distances, that's where the Care 6 HDB input and output cards become absolutely essential.
HD-based D. Okay, for listeners maybe not familiar, this is using standard network cable like CT6 for video, right? What's the big advantage here?
Simplicity and reach, mainly. K6 cable is relatively inexpensive. It's often already installed in buildings, and it's easier to terminate than, say, fiber. Plus, a key feature these WolfPack systems leverage is HD-based receivers with PoE power over Ethernet. Meaning the small receiver box that sits behind the display, maybe hundreds of feet away from the main switcher rack, doesn't need its own separate power brick and power outlet. It gets its power directly through the same K6 cable that's delivering the video and audio signal.
That's huge for clean installs. Less wiring clutter behind potentially dozens of screens.
Exactly. But there's a crucial technical detail, a trade-off, mentioned in the source material we need to highlight. The specs state that using K6, these systems support 1080p resolution video extension up to 330 feet.
Okay, 330 feet for 1080p. What about the full 4K 60 signal we started with?
That's the catch. Pushing the full uncompressed 18 GBPs needed for 4K 60 4.4.4 over standard CD6 beyond, say, maybe 100 feet or so, is extremely challenging with current HD BASI standards. It often involves compression or limitations. So if you absolutely need that pristine 4K 60 quality at the full 330-foot distance, C6 HDBC might not cut it. You'd likely need to look at fiber optic extension, which is another layer of complexity and cost.
That is a really important distinction for anyone designing these systems. So 330 feet is solid for HD, but 4K at that distance over CT6 is a maybe or requires compromise.
Precisely. It forces a design decision based on the specific requirements for each display location.
Got it. Now, regardless of distance, let's talk speed again. Not data rate speed, but responsiveness, control speed. How quickly can an operator switch views? How quickly does the image actually appear?
This is where high-end matrix switchers really differentiate themselves. The specs list two key metrics here. First, latency, the time it takes for the signal to actually travel through the switcher from input to output. That's listed as 100 milliseconds.
Okay, 0.1 seconds.
Right. And second, the switching speed, the time it takes for the matrix to physically change the connection, like going from showing source A to showing source B on a specific screen. That is also listed as 100 milliseconds.
Wow, okay. 1/10 of a second for both signal travel and the actual switch command execution. In a high-pressure situation, like an emergency operations center, what does that 100 meters feel like? Why is that number so critical?
To a human operator, 100 milliseconds feels effectively instantaneous. There's no perceptible lag between hitting a button to change a view and seeing that new view appear. Think about air traffic control, security monitoring rooms, trading floors, any environment where decisions are made based on real-time visuals. If there's a noticeable delay, say half a second or more, it can introduce cognitive lag, confusion, or delayed reactions. It undermines the whole point of the system.
So that speed isn't just a nice to have, it's fundamental to the system's purpose.
Absolutely. And it has to maintain that speed consistently, even if you're switching all 18 outputs at the same time. They all need to update in near perfect sync.
Makes sense. And how do users actually interact with this? How do they control which source goes where on such a complex grid?
Control options seem quite diverse, catering to different needs. There's remote control via apps, presumably mobile apps, and a secure Web GUI, like a browser interface. That's good for integrated systems or control from a central desk. But for operators who need direct, immediate control right at the equipment rack, there are physical options too. The front panel has either a touchscreen or physical buttons, depending on the configuration. And the specs also mention optional hardware. Dual 7-inch color monitors built into the chassis, likely for previewing sources or confirming outputs right there.
So a mix of network and physical control.
Flexible.
Okay, let's pivot to the configurations themselves. Since it's based on this modular 18 by 18 chassis, people aren't just buying one fixed box, are they? How does the pricing work?
Yeah, it reflects that modularity. You're essentially buying the core capability and then scaling the inputs and outputs as needed. The source material shows that the base unit, the build-your-own 4K 60 4.4.4 HDMI Matrix switcher, basically the 18 by 18 chassis ready for cards, starts around $1,500.
Okay, so that's the foundation.
That's the foundation. Then you add the specific input cards, HDMI or HD-based, and output cards, again, HDMI or HD-based, you actually need for your project. The sources also give examples of pre-configured systems to show how the price scales with density and features.
Like what?
Well, there's a WolfPack 4K 60 4x8 HDMI Matrix switcher listed at about $3,300, so 4 inputs, 8 outputs. Then a 4K 60 4x18 HDMI Matrix switcher, same 4 inputs, but maxing out the outputs is around $4,800. And a higher-end one, a 4K 60 5x18 configuration, jumps up to about $7,100.
So the price climbs significantly as you add more populated ports and potentially more features.
Exactly. And it's important to look at the descriptions for those pre-configured models. They often explicitly mention that features like the integrated video wall processing, the scaling, app control, and even separate audio handling are included in those bundles. So you're not just paying for ports, you're often getting those advanced processing capabilities built in once you go for a specific pre-configured setup.
Right. So tying this all together, what we're seeing is a convergence. It's about handling that massive 18 Gbps bandwidth.
Yep, maintaining the strict HDCP security.
Adding flexible internal processing like scaling and flipping.
Offering different physical connection options like HDMI and HD Basic with PoE.
And doing it all with incredibly low 100 millisecond latency for both signal travel and switching.
That's the package. That combination of high bandwidth, security, flexibility, and crucially, that near instantaneous speed and reliability, that's what defines these systems for demanding environments.
Okay, so let's leave you, the listener, with a final thought to chew on. We identified a key technical trade-off. Getting that pristine 4K 60 signal reliably over long distances using standard SCSI cabling is tough, often limiting you to 1080p for runs like 300 feet. Yet these matrix switchers offer lightning-fast 100 millisecond switching. So considering the significant cost and the mission-critical nature of these deployments, which specific high-stakes environments do you think would prioritize that instantaneous 100-meter switching, even if it meant potentially compromising on sending full 4K resolution to distant displays? What's the real operational cost or risk of not having that sub-second switch? Where does speed trump ultimate resolution? Something to think about.